Hello, good afternoon, my dear student. Today we will repeat experiment 2, verification of maximum power transfer theorem. We will perform one more new experiment, that is determination of different parameters of two-port network. Determination of different parameters of two-port network in next lab class. Okay, today we will repeat experiment 2, verification of maximum power transfer theorem, but in next lab class we will perform experiment 7, that is calculation of different parameters or determination of different parameters of a two-port network. I will cover the theory part of a two-port network in next theory class. After that you can perform. Okay, without theoretical concept you will face lot of problem to perform experiment 7, that is determination of different parameter of a two-port network, Z parameter, Y parameter or impedance parameter, admittance parameter, mix parameter, etc., and we will try to understand their interrelation. Okay, but now I suggest all of you to perform experiment 2, verification of maximum power transfer theorem, and you tell me about your result. Okay, if you face any difficulty or problem to perform this experiment, because you have already you have already performed, you have already executed this experiment, but you try to complete it yourself. Okay, because that time I have explained different steps, and with my instruction you actually completed the experiment. Now you do it yourself. I am sharing the link here. You see the chat box. Everyone, Dibbojyoti Roy and others, please take the link which one I have given in chat box, and you use this link to perform this experiment. Basically, today we will try to understand different question. Okay, different question which can arise for this experiment. Okay, I mean, associated with this experiment. First, you complete the practical part. Later on, I will ask you some question or a quiz on this experiment. Experiment number 2, verification of maximum power transfer theorem. So now everyone do the experiment, perform the experiment yourself, and let me know the result. Okay, and then I will ask you some question related to this experiment, and in next lab class we will perform a new experiment, that is determination of different parameters of a two-port network. First I will cover the theory part in next theory class, then we will perform the experiment number 7. Okay, uh, let me show you the steps which are required to perform this experiment. Okay, let me show you the procedure part. Okay, you know the steps required for this experiment, but You see the slide 2 where I have given the steps which are required for this experiment. Okay, so everyone, I suggest to all of you, complete the experiment yourself and write in your chat box, particularly you write the value of load resistance for which you you will get the maximum, you will get the maximum uh, I mean maximum efficiency, maximum power, sorry, maximum power. Okay, you tell me the value of load resistance for which maximum power will deliver from source to load. You just see the figure here. Okay, so you everyone do the experiment yourself and write the value of load resistance RL for which you will get the maximum power at load side. I mean the source under this condition, the source can deliver maximum power to load. Okay, maximum power to load. So your load power versus load resistance curve must be look like this, like a parabolic bell shaped curve. Okay, like a bell shaped curve, parabolic, like a bell shaped curve, symmetric curve with respect to R TH, with respect to source or input resistance of the circuit or Thevenin resistance of the circuit. At Thevenin resistance, you will get the maximum power at the load side, that is 50%. So therefore, you will get a symmetric curve about load resistance equal to Thevenin resistance RTH. So I suggest you do the experiment and write the value of RL for which 50% power or maximum power will be delivered from source to load. From source to load. And you know there is a confusion between power transfer efficiency and maximum power. Okay, so that's why I have given the curve efficiency versus load resistance. You see, efficiency, maximum value of efficiency is 1. Efficiency is nothing but the ratio of load power divided by total transmitted power, that is load power plus source power. Okay, so don't make a confusion between load power and the efficiency of the circuit. Load power and the efficiency of the circuit. Efficiency, the maximum value of efficiency is 1, but maximum value of load power is half of the source power, 50%. Okay, so you perform the experiment and write the value of load resistance for which you can transfer maximum power from source side to load side. Okay, now we have already done this experiment. Yes, you have done this experiment. You repeat this experiment and you tell me the value of RTH. RTH. Uh, yes, everyone has completed this experiment. This is experiment number 2, verification of maximum power transfer theorem. Okay, you repeat this experiment. I will ask you some question related to this experiment as a quiz. Okay, but before that you inform me about the value of RL for which you get the maximum power at load. That means the source can transfer or deliver maximum power to its loads. Okay, you do it. You tell me the value of RL, load resistance. Then I will ask you some question. Okay. In next lab class, we will perform the new experiment, that is experiment number 7. This experiment is based on two-port network, but we actually do not cover the theory part of two-port network. Okay, so I will complete the theory part of two-port network in next theory class, that means Monday or Wednesday. After that, in next lab class, you will perform the new experiment related to two-port network, determination of different parameters of a two-port network, impedance parameter, admittance parameter, hybrid parameter and mix parameter. We will discuss those topic in next theory class, and then we will verify the value of these parameters experimentally. But today you repeat the experiment 2, verification of maximum power transfer theorem, and you tell me the value of load resistance for which you will get the maximum power at load side. I mean, source can transfer or able to transfer maximum power to its load side. Okay, now you do it yourself. Now let me ask you some question related to this experiment. Okay, if you, the first question for all of you is, if load resistance is equal to Thevenin resistance of the circuit, then what will happen? Then what will happen? My question is, if load resistance is equal to source resistance, okay, if load resistance is equal to source resistance, then what will happen in your circuit? If RL equal to RTH, okay, the Thevenin resistance and internal resistance of the circuit, then what will happen? What will happen? Okay, in what will happen? Origin maximum power will be transferred. Maximum power will be transferred. Origin has given answer that maximum power will be transferred. About others, what will happen if load resistance is equal to the Thevenin resistance? You have already completed this experiment, but you have some doubts, okay, about this experiment. You tell me what will happen if RL equal to RT. Orijit, your answer theoretically we have proved that maximum power will be transferred for source side to load side if RL equal to RTA. But if you select load resistance equal to Thevenin resistance and source resistance of the circuit, then maximum power will deliver. Then what will happen? Maximum power deliver means your circuit will produce a maximum amount of heat. Your circuit will produce actually power will be dissipated through load resistance as a heat energy. So if your circuit produce huge amount of heat or maximum heat, then what will happen? The circuit will damage or the circuit will burn out. Theoretically, maximum power will transfer, efficiency will be 1. It will become very efficient. Efficiency, okay. The Saivaraj, Nivedita, Orijit, your answer, okay, your answer is correct. I mean, all of you are correct theoretically. But if you select load resistance equal to Thevenin resistance, practically, then what will happen? In real time, then maximum power will deliver. As a result, maximum heat will produce in your circuit, which will burn out the circuit element or damage the circuit. So therefore, if we consider load resistance equal to Thevenin resistance in real time or real circuit, then the circuit will get damaged due to heating effect. Due to heating effect. Everyone, please note down this point. We cannot select load resistance equal to source internal resistance of the circuit, that is Thevenin resistance, in real application, because the circuit will get damaged due to heating effect, because maximum power will transfer from source to load. As a result, maximum heat will produce in your circuit. So therefore, we never select load resistance equal to source resistance in real application of any circuit. Real application of any circuit. Okay. So can you tell me a real application of this theorem, maximum power transfer theorem? A real application where we directly use this concept to design a circuit. We use this concept. Can you tell me the application field? What necessary steps should we take to get efficient output without any damage of circuit? Yes, Orijit. Then what we'll do to overcome this difficulty? Okay, to overcome this difficulty, I mean to avoid this problem. What we will do? Anyone can answer this question? Anyone can answer? If load resistance equal to source resistance in real application, then circuit will get damaged or burned out due to heating effect, because maximum power transfer from source side to load side, then what we will do? We use in communication system to get a good output signal. Thank you, Saivaraj. Your answer is correct. Yes, we design a circuit based on maximum power transfer concept in communication. Okay, to transfer maximum information from source to load, from transmitter to receiver. Okay, and also microwave. Okay, microwave field, it is also associated with communication, no problem. And power electronics, obviously this concept is also used in the field of power electronics. Okay, the application of this theorem is in the field of power electronics, in the field of communication, microwave, etc. Arijit, actually your question is that then what we will do to overcome the damage effect of our circuit due to due to huge amount of heat. Okay, anyone can answer this question? The application of this theorem, real application of this theorem. My next question, second question is, what actually are the application of this theorem, of this concept? So Saibaraj has given answer that in communication field, also power electronics field, to transfer maximum information from transmitter side to receiver, or maximum power from source to load in power electronics. Okay, now you tell me the answer of second one. Answer of the second, Arijit Acharya question. How do we overcome this problem? How do you overcome this problem, heating effect? If anyone can give answer of this question, okay, let me tell you the answer. If you consider the load resistance, the value of load resistance is higher than that of source resistance or Thevenin resistance of the circuit, we can overcome this problem. So to avoid the burn out effect or damage effect of the circuit, we must select the value of load resistance is greater than that of the source resistance. I mean RL must be greater than RTH. Okay, RL must be greater than RTH. Then you can avoid the heating effect. But in that case, the efficiency would decrease. Yes, efficiency we can tolerate the efficiency part. But actually, if you consider the efficiency part, then what will happen? Your system will get damaged. Then that means you cannot execute your operation. You cannot execute the function. You cannot perform the uh, your experiment, I mean. Okay, if you consider the efficiency part, if you want to get higher efficiency by considering RL equal to RT, at that time your system will get damaged. Therefore, you tolerate with efficiency, you consider less efficiency, no problem, but you must, okay, uh, avoid the damage effect or burned out effect of your circuit. Okay, this is the main point for this uh, theorem, or for any real-time application. We must tolerate the efficiency part. We will consider less efficiency, but we never consider a burn out effect or a damage, permanently damage effect in your circuit. Okay. RL less than RT is, if you put RL less than RT, then you see the curve. Then you see the curve. If RL less than RT is, then what will happen? You will get your system will work, and you will get efficiency less than 50%. You see the graph. If you see the graph, you see this is RL equal to RT is, here RL greater than RT is. This case, this portion, just uh, left hand side of this peak value, you see here RL less than RT. This is the value of RT is this value. RL. So your system will work, no problem. Your system will work, okay, and you will get power, no problem. Less than maximum power, maximum. But if you consider RL load resistance greater than RTH, then you will get near about, very close to the maximum power, less than maximum power, but very close, okay. So you can consider, no problem, origin, you can consider RL less than RT, your system will work, okay, your system will work. But if you uh, in case anyhow you know that the circuit has many effect. If you apply supply voltage to the input of your circuit, ambient temperature of your circuit you must be considered, okay. If temperature of your circuit is increases, then there is a probability of heating effect, and as a result your system will get damaged. So therefore we will prefer the load resistance is always greater than RTs, okay. At this, under this condition, if I consider RL greater than RT, then whatever the ambient temperature, this will not affect the performance of our circuit, okay. Arijit, surrounding temperature or associated with your circuit, okay. Now let me ask you one another question. If your circuit is a pure resistive circuit, then you can say that maximum power will transfer to load from source if RL equal to RT is. Now you consider your circuit consists of uh, inductance and inductor and capacitor along with resistor, okay. In this case in experiment number 2, we have considered a pure resistive circuit to verify the maximum power transfer theorem, but in real application sometimes we need a circuit which consists of resistor, capacitor and inductor. Resistor, capacitor and inductor, or resistor, capacitor or resistor, inductor. I mean first order circuit or second order circuit, okay. In real application we face such type of circuit. We actually use such type of circuit, RL circuit, RC circuit, RLC circuit. We have covered the theory part of this circuit, okay. Now if your circuit consists of resistor, capacitor, inductor, okay, then what will be the condition for maximum power transfer? What will be the maximum power transfer condition for a RLC circuit or for a RLC circuit? Anyone can give the answer of this question? if your circuit is not a pure resistive circuit, your circuit consists of resistor, capacitor and inductor, or resistor, capacitor only, or resistor, inductor only, or both. Then what will be the maximum power transfer condition? Or is it ZL equal to ZTH? ZL equal to ZTH, load impedance is equal to Thevenin's impedance. What about others? Anyone? Saiva, Nivedita, Amit. What about other student? Tell me. Orijit has written that ZL load impedance Thevenin impedance. Load impedance offered by each circuit element should be equal to ZTH. Other student, write your answer. Yes, Z will equal to ZTH. Orijit, Nivedita, Saiva. Okay. You just check your answer. You have written ZL equal to ZTH. These impedance terms are complex terms. Okay. It has a real part and also an imaginary part. Okay. So you know that I have proved in theory part for a RL circuit or RLC circuit, what will be the condition? For this case, you know that there is a real part and also an imaginary part associated with the impedance. For real part both will be same, and imaginary part, what will happen for imaginary part? They will be complex conjugate to each other. Start, it will be, yes, actually you will take magnitude, complex conjugate, yes, complex conjugate, ZL mod equal to ZTH. You must correct your answer, Nivedita, Orijit. Don't write ZL equal to ZTH because these factors are associated with real part and imaginary part, and we have proved that for such type of circuit real part must be same, real part of ZL and ZTH must be same, and imaginary part will be complex conjugate of each other. Mod of ZL equal to mod of ZL. Right. Now your answer is correct, Orijit. Mod ZL, magnitude of load impedance must be equal to magnitude of Thevenin impedance or internal impedance of the circuit. If you write ZL equal to RL plus ZXL and ZTH is equal to RTH plus JXTH, then they will be complex conjugate of each other. Yes, Nivedita, your answer is correct. Okay, so for a RLC circuit, RL circuit or RC circuit. Okay, so for such type of circuit, you know that impedance terms appears, impedance instead of resistance, and impedance has two parts, real and imaginary. So for maximum power transfer, the magnitude of load impedance is equal to magnitude of internal impedance of the circuit, or you can write complex conjugate. Load impedance must be complex conjugate of Thevenin impedance. Okay. Any doubt? Okay. I hope everyone understand the condition for maximum power transfer for a RL circuit or RC circuit or RLC circuit instead of pure resistive circuit. Okay. Okay. Now tell me another question. If for a communication circuit, real-time application, communication, power electronics, for you know that to get message or information from transmitter side, you use an antenna. I mean, an antenna is used to interface between our TV receiver I mean TV setup and the broadcasting information or message through an antenna. Okay, antenna is used as an intermediator between TV set and the transmitter. Okay, through antenna we actually receive the transmitted information. Okay, and this transmitted information is connected to the receiver setup. Okay, now if the antenna impedance, then what we'll do to get maximum information from transmitter side and to deliver receiver side? How do you arrange your antenna to get maximum information from transmitter side and deliver to receiver side? Okay, the question is that what will be the arrangement of antenna? What will be the arrangement of antenna which will provide maximum information to receiver side from transmitter side? If and another question, when maximum power information and message transfer from transmitter side to receiver side through antenna, then what is actually the phenomenon, the condition is the condition when maximum message transfer from transmitter side to receiver side through antenna, then this is called perfect match condition. Okay, perfect match condition, source to load. Okay, perfect match condition. How do you actually obtain the maximum perfect match condition? Actually, my question is that how do you arrange your antenna to get maximum information from transmitter? Okay, how do you arrange your antenna? You know, antenna is used to make an interface, okay, between transmitter side and receiver side. Through antenna, you transmit message from transmitter side to your receiver. Then if you take example of your TV set, so your TV set, you actually uh, extract the information, broadcasting information from any transmitter side, okay, through antenna. How do you arrange your antenna to get maximum information? Okay, or when you will get maximum information under match condition or unmatched condition, match condition or unmatched condition, or critically matched condition. Under match condition or critically matched condition or under match condition, you think yourself and you give the answer. Okay, you give the answer. Now origin match condition. Match condition means there is no feedback. There is no feedback between load and source. Let me explain this thing. Suppose you connect a supply voltage to your circuit. Okay, then this supply voltage, the current corresponding to supply voltage, will reach to your load side. Okay, and you will get a load voltage. Okay, and you have seen through this experiment, verification of maximum power transfer theorem, that maximum power transfer from source to load if RL equal to RT. That means this is match condition. Okay, there is no loss of power. Due to feedback from load. Okay, understand this point? When your load resistance equal to Thevenin resistance, then maximum power transferred to load. That means there is no loss of power. Okay, due to feedback. There is no reflection of the signal from load side. Whatever coming from source side, that actually totally absorbed at the load side. Okay, whatever the power coming from source side to load side, load absorb that amount of power. There is no feedback. Okay, I mean load does not reflect back any power. Okay, so such situation is known as match condition. M-A-T-C-H-E-D. Such condition is known as match condition. Okay, I hope you understand what is match condition. Match condition means there is no feedback from load to source. Okay, whatever power comes to the load side from source side, the total power absorbed at the load. Okay, then okay, you understand the match condition. I suggest all of you please understand the match condition. My question is now, how do you arrange your antenna to get maximum information from transmitter? Because if your receiver side, for example your TV setup, if you get less information, then what will happen? You will get a hazy picture, or you will hear a unclear sound. Okay, if the broad whatever coming at your TV setup through antenna, this information actually is not same as the transmitted information. Then what will happen? You will see, if you consider video information or audio information, then you will see for video information a hazy picture. Okay, your video will be hazy, and if you consider audio case, then you will hear an unclear sound. Okay, because the information or message whatever coming from transmitter side, that is different from the information appear at TV setup or receiver side. Okay, this situation is known as unmatched condition. So my question is, how do you arrange your antenna to get maximum information? I mean, whatever information transmitted, you want to extract or collect that amount of information. Then how do you arrange your antenna? This is my that is my question. Okay. Anyone can give answer of this question? Actually, the answer is that you will arrange your antenna in such a way, I mean with such desired specification, that you slightly more than match condition. No, under match condition for this case. Under match condition, more than match condition, but for this case you need to use with match condition. Under match condition you will get maximum information. Okay, maximum information for match condition. You will consider or you will arrange your antenna in such a way that the transmit receiver impedance and antenna impedance must be same, must be equal. You will make a match condition. Okay, now let me ask you another question. What will be the power? What will be the expression of power? What will be the expression of power? Load power expression. For this case, hitting actually receiver antenna nowadays, receiver use integrated circuit component IC, very small size. Okay, so that's why the impedance of this circuit and antenna impedance is not very high value actually. So therefore, heating effect is you can neglect for this case. If you consider power electronics case, then heating effect is very high because the impedance is very high. Impedance is very high for power electronics case. If you consider the power line case, suppose the connection of your house, okay, wire connection of your house. Uh, Wire connection of your house through transformer. Okay, that time you need to consider the heating effect, because for this case load resistance and source resistance is very high. Okay, because here we generally use discrete bulky component actually, so their corresponding heating effect is very high. Okay, but in communication we use miniature size component, integrated component or discrete component. So therefore their corresponding impedance or resistance is very less. As a result, their corresponding heat is also less. So we can neglect, we can tolerate the heating effect for for communication, transmit for receiver. Okay, receiver consists of discrete component, integrated component. Okay, so that's why, so for power electronics you must consider discrete components. For example, discrete components, you can say that a if you consider a resistive circuit, inductive circuit, capacitive circuit, or combination of these components are discrete component. But if you design a circuit on a single IC, integrated circuit, single IC, okay, small size IC, and on that wafer or chip you can design a number of components. Okay, these components are called integrated component, but individual component is known as discrete component. Individual component is known as discrete component. Okay, uh, and let me ask you one more question. Power expression of power. So you can derive expression of power for load resistance, also source resistance. Okay, load resistance and also source resistance. Okay, uh, source resistance. Okay, it's okay. If you have any doubt or question related to this topic, you can ask me. If anyone has any doubt or confusion or any question related to this experiment, you can ask me. Okay, you can ask me. Saivaraj, okay. Anyone? Dibbojyoti, Arijit, Nivedita, Amit, and other student. Okay, then I hope everyone understand the experiment. Okay. Uh, in next lab class, we will perform experiment number 7, determination of different components of a two-port network, impedance component, impedance parameter, and admittance parameter. Okay. So thank you everyone. Let me stop today's lecture here. Everyone write your roll number, okay, for the purpose of attendance.